today's trending cryptography, modern cryptography. So if you have any doubt at any point of time, because it's somewhat lengthy process, without understanding the basic terminology, it is not possible to get into the perfect idea of DS and AS. Okay. If you have any doubt, you please stop me. Am I audible to you clearly? Am I audible to you?
Yes, ma'am.
See, today's concept is a modern symmetric cryptography. The first well-known cryptography. Okay, so today we're going to discuss about the next part of the first unit. In the first unit, we have three parts. Part one deals with the basic terminology. Just for time being, I skip, but I will take just before the CA. Second part of the cryptography is a symmetry cipher, classical cipher. Okay, so we have completed. The third part of the cryptography is a modern symmetry cipher, DES. Okay, so we are going to discuss about a modern symmetry cipher, modern cipher. Modern symmetric cipher, well-known cipher, DES. Okay, so DES stands for Data Encryption Standard. DES stands for Data Encryption Standard, developed by IBM, standardized by NIST. Okay, developed by IBM, not by the NIST. Okay, but the AES is standardized and developed by NIST. Okay, it's for government purpose. But IBM, the third party vendor, designed this ES in the year 1977. Sorry, 1967. So we'll talk more. We'll discuss about DES today, and forthcoming 5 classes. We're going to discuss about this DES alone, data encryption standard. Okay. But before getting into the idea of DES, as a cryptographic learner, you have to understand something. In cryptography, there are so many algorithms: RSA, elliptic curve, Elgamal, DES, AES, SHA, MAC, so many things. Okay, learning each and every component is important because, for example, if you take a HTTPS is based on AES. Okay, so you should understand AES. Then only you can understand the working principle of HTTPS. Okay, so you have to understand each and every component. Okay, but learning the design aspect of component is something important. In simple thing, I can say like this. Learning the preparation of rasamalai or rasagullas is good, okay, but all those things are based on basic design aspects, basic ingredients, basic components. Okay, if you can understand the basic design aspects, then you can design your own recipe. You can come out with your own recipe that is required for cryptography. Okay, only from students' mind can think in a different manner. Okay, so you can come out with a new technology only if you can understand the design aspects, not by understanding working strategy of DES. It's not possible to develop a new crypto system. Okay, so that's why DES is based on a powerful structure called Feistel structure. Okay, AES is based on a powerful structure called Rendon structure. I'm repeating again. Am I audible to you? Should I switch off the fan? Am I audible to you clearly? This is
Audible,
audio.
ma'am. Yes, ma'am.
So this DES is based on the powerful cryptography structure called the Feistel structure. Okay, Feistel is not a cryptography; it's a structure. AES is based on Rendon structure. In this manner, most of the algorithms are based on the design aspect. For example, even if you can take a hash algorithm, SHA, secured hash algorithm, that is also based on a structure called the Merkle-Damgard structure. Okay, so all these cryptographic primitives, all these cryptographic algorithms, successful cryptography algorithm. Okay, we have so many cryptography, symmetric cryptography, but what is the reason for learning DES? Because it's successful. Okay, it has 20 years of excellence. It was developed in the year 1967. The first attack against the DES was happening only 97. Okay, so 20 years of excellence. So unbreakable crypto systems were developed based on some design aspects. Okay, but that's so simple. But if you can understand the design aspect, then you can come up with your own crypto system. That is required for BTech professionals. Okay. So the DES is based on the crypto principle called Feistel structure. Okay. So slowly I'll move on to this. Actually, today we are not going to start the DS. The design aspect of DS, all the motivating idea behind the symmetric cryptography. So we discuss all those things, then we slowly get into this DS. Okay, and you have to understand one more difference. Okay, symmetric or asymmetric cryptography. If you take asymmetric cryptography RSA, it's still unbreakable. It's also having 30 years of excellence. 1977, it was developed in the year 1977. It's still unbreakable, but that is, I can explain RSA with the two lines of state. Okay, I can explain elliptic curve with the two equations. That's simple. Okay, because asymmetric cryptographies are strongly built on top of mathematical model. It's a strong mathematical model. Okay, RSA is based on strong mathematical model Euler's theory. Elliptic curve is based on strong mathematical model DLP. Okay, so if you can understand elliptic curve or DLP, then understanding DSA is not at all a matter. RSA is not at all a matter. But the symmetric crypto system, TS, AES, all these are not so simple like this. Okay, it's not based on single equation, because in asymmetric cryptography, we need a linear property, linear relationship between the plain text and ciphertext. But for symmetric cryptography, we have to break the linear relationship between the plain text to ciphertext, because if there is a linear relationship, anybody can break it, can solve it. Okay, so we have to break the linear relationship between the plain text and ciphertext. So it's so complex based on so many rounds. So to understand the design aspects of DS, you need to work on, you have to concentrate for 6 to 7 hours of lectures. Okay, so then only you can build a similar kind of architecture, so complex in nature, based on various levels of add-ons in terms of substitution and conjugation. Okay, so it's so complex as compared to RSA or elliptica or algamma. Okay, so before getting into that, I will also conclude one thing. We have two systems, symmetric system and asymmetric system. Okay, you cannot say that asymmetric system is better than symmetric or symmetric system is better than asymmetric. Okay, for the particular scenario, symmetric is suitable. For particular scenario, asymmetric system is suitable. For example, if you want to safeguard the system for a fraction of the time, okay, data in security, data in transit security, definitely it requires asymmetric cryptography. Okay, but for data in rest security, the data will be available for long period of time. The hacker intruder can capture the data, can use the data for a long period of time, even in years. Okay, but still it should be unbreakable. Okay, so that is the design idea behind the symmetric cryptography. So symmetric cryptography is suitable for data in rest. Okay, the hacker, intruder, cryptanalyst will get enough time, even in years, to break this. Okay, but asymmetric cryptography, the data will be transferred for the fraction of the time, milliseconds or microseconds. Okay, hacker or intruder need to break the crypto system in terms of millisecond or microsecond. So that is the design aspect of asymmetric cryptography. Okay, so the design aspects, symmetric cryptography is different, asymmetric cryptography is different. Both are powerful in different perspectives. Okay, so the first modern symmetric cryptography standardized by NIST is the DES. Okay, so as I said already, it is based on a structure called a pizza section. Okay, so pizza section is based on a simple structure by ESTL. Feistel structure. Okay, Feistel is a person, German mathematician, developed a structure. So what is this Feistel section? Actually, if you take symmetric cryptography, I already given two different variation. One is known as a block cipher, another one is known as stream cipher. Okay, so the block cipher, it works on a block of data. Okay, if you take any encryption algorithm, symmetric cryptography encryption algorithm, it takes a plain text in terms of block. Okay, so modern symmetric cryptography, it works on a block of binary data. Okay, binary bit stream. So the plain text for DES, it works on a block of size 64 bit. AES works on a block of size 128 or 196 or 256. Okay, so sorry, AES works on 128 bit block size. So another input is key. Key is also a block. Okay, binary block of size m bits. Okay, produces the cipher output. Okay, cipher output is of size same size of plain text. Okay, the plain text is a 64-bit block. Ciphertext is also a 64-bit block. Okay, so the modern symmetric ciphers are block ciphers. Okay, by nature it is a block cipher. Modern symmetric ciphers are a block cipher by nature. But we can also apply it this border symmetry cipher for stream related processing. Okay, so for that we have to change some sort of mode of operation. Okay, so the different operating mode, the initial design aspect of border ciphers are block ciphers, but we can also use it as a stream cipher, but changing some parameters. Okay, but the basic thing is all the modern symmetry ciphers are block cipher in nature. Okay, so it works on a block of data. It works on a block of binary data. Okay, so DS works on 64-bit blocks. It produces the output of 64 bits, and its key size is 56-bit key size. Okay, so the first understanding required here is a block cipher, and all the symmetry ciphers are product cipher. Okay, product cipher. What is a product cipher? The same operation or different operation to be repeated for n number of times. Okay, for example, the plain text to be given to the functioner. Okay, this is a single operation. If this is a cipher, this is not a block cipher. Okay, so the output of this is given to the same function again. Okay, so now here the function is repeated twice. The output of the plain text, sorry, output of this f of p is given as the input of the function, same function. Again, this is given to the function. So this type of cipher is known as product cipher. Okay, so the same function or different function to be applied again and again on the transformed data. Transformed data. Okay, so this is actually a product cipher. This type of cipher is a product cipher. All the symmetry ciphers are product cipher. All the symmetry ciphers are modern symmetry ciphers are block cipher. Okay, so if you take any block cipher, if you take any block cipher, for example, let me take a block cipher, block of size 2 bits, very simple block of size 2 bits. Okay, so now the block cipher should exploit the property called a non-singular property. Okay, it's not only for symmetry cipher; it is required for all the asymmetry cipher. Non-singular property. What is that non-singular property? Non-singular property is nothing but reversibility. Okay, reversibility. For example, if you take 2-bit input, the plain text is a 2-bit data. Output is also a 2-bit data. For example, this encryption algorithm provides a transformation like this. Okay, possible plain text are 00011011. Okay, and it is transformed as 00 is transformed as 10101, maybe 1110. This is 01, and 11 is also 0. Okay, so each 2 bits transform into another 2 bits. Okay, but here this, just if you observe this, okay, 00 is converted into 10. Okay, if the ciphertext is 10, it is reversible. We can convert that one into 00. Okay, but take it out. This case 10 and 11 transformed into a same 2-bit button 0. Okay, so if the input is 10, the encryption function will produce the output as either 01, oh, sorry, 01, and the decryption function, there is a possibility of two things. The output may be 10 or 11. Okay, so here the conflict occurs. This conflict should not be the characteristics of any symmetry cipher. Okay, so if there is a conflict like this, then this cipher is not reversible. There is no reversibility here. Okay, so there is no reversibility. Okay, it is not possible to get back the plain text as it is. Okay, so reversibility is a required property. So one-to-one mapping is required here. One-to-one mapping. Okay, so non-singular property. So once 10, it is converted into 01, and 11 possibly should be 00. So one-to-one mapping is required. So this one-to-one mapping is known as non-singular property or reversibility. Reversible. Okay, reversibility. So if there is no non-singular property, if the bit pattern is not reversible, then that particular type of transformation is not suitable for security, cryptography. Okay, clear? Can you understand non-singular property? Non-singular property is the most important property for any symmetric or non-symmetric, sorry, asymmetric cryptography. Okay, clear? Okay, so that is a first idea, first important thing. need to discuss about a block cipher non-singular property. Okay, so let's get into this another thing. If you take this transformation, 2-bit transformation, 0 0 is transformed into 1 0, 0 1 is transformed into 1 1, 1 0 2 is transformed into 0 1, and 1 1 is transformed into 0 0. So there are possible combinations of, okay, only 4 options are available. Let's just get into further thing. A block of size 4 bits. Block of size 4 bits. Okay, so if you take 4-bit blocks, the possible transformations are possible plain text combinations are 0 0 2 1 1 1 1. Okay, so now we can do the mapping. The input will be this. Okay, output is also one among this. Okay, one among 16 combination. Okay, so I can simply design the concept like this. The input will be a 3-bit data, bit 0, bit 1, uh, bit 2, and bit 3. Okay, so output is also a 4-bit data. So this will be the 0 prime, transform the data, B1, second bit to be transformed, and third bit to be transformed. Okay, B1 prime, B2 prime, and B3 prime. Okay, so in between there should be a transformation required. Okay, so very simple transformation here is, okay, very simple transformation I can do here is, so this is a 4-bit binary. The possibility is 16 different possibilities. So 0, 1, 2, 3, 4. Because this 4-bit number can be represented in terms of a decimal number between the range 0 to 50. So 16 combinations are available. Okay, so this one to be correspond to, because 1-to-1 mapping is required. So this can be again 0, 1, 2, 3, 4, and so on. Okay, so each input randomly to be connected with one output. Okay, each input to be randomly connected with one output, randomly. Okay, so each input to be randomly connected to one output. That should be 1-to-1 map. Okay, so if you take this, if the input is, let us take this, the input is 1, that is 0 0 0 1. Okay, it is connected with the 4. What will be the output? Output is 0 1 0 0. Okay, if the input is 0 0 0 1, output will be 0 1 0 0. So based on this transformation, okay, so this is actually based on Feistel. It is declared as the ideal cipher. Okay, so why it is ideal cipher? Here there is no key at all. This transformation is unique transformation is a key. Okay, so this is one single transformation. Okay, if you want to break this triple system, you have to try all the different combinations of transformation. How many transformations are possible with this case? How many transformations are possible with this case? How many such transformation, how many such random connectivities are possible if you take 4-bit input? Please interact with me.
15 factorial.
Huh? Again, come again.
15 factorial.
Ah, yes, perfect. 16 factorial. Or I can also define like this. Um, 2, because it's a binary bit pattern. Okay, so 2 power 4, the whole factorial. Okay, can I write like this? 2 power 4 whole factorial. Can you understand why I have written like this? Why I have written like this? One single transformation is how many transformations are possible? One single transformation, 4-bit binary. So each sample to be expanded into 16 different combinations, because it starts with 0. Okay, if it is 4 bits, 2 power 4. If it is 2 bits, 2 power 2, 4 combinations. Okay, if it is 4 bit, 2 power 4 combination 16. If it is 5 bits, 2 power 5 combination, 32 combinations are available. Okay, so let it be general. 2 power n factorial combinations transformations are available for n bit inputs. Okay, 2 power n factorial transformations are available for n bit inputs. Okay, so this is a very big, if n is high, then this is a very big transformation, very big space. Okay, so if n is 4 bit, it's breakable. Okay, it's breakable with the normal computing power. If n is 64 or if n is 128, then 2 power to 128 factorial transformation, trying all those transformations is completely impossible. Okay, that's why it is known as, it is declared as ideal cipher. Ideal cipher as Feistel. Ideal cipher, okay, it is declared as ideal cipher by Feistel. Okay, but it is a simple utopian cipher. It is something imaginary. It is not possible to get into the real sense. Why? Because this transformation, if you take 4-bit data to create one single transformation, how many bits? How many bits are required? One single transformation. How many bits are required? So 4-bit data, okay. So into 16 different combinations are required. So 4 into 16. So this is a key size for 4-bit inputs, okay. But 4-bit input is not suitable. You have to take n of 64-bit data or 128-bit data, okay. If it is 64 or 128, how much amount of data you have to remember? 4 into 64 or 4 into 128. Okay, so that much amount of data, remembering that much amount of data is completely not possible. Remembering the key with um, with that wider space is not possible. Okay, so that's why it is known as imaginary cipher. It is ideal cipher. It is unbreakable, but you have to remember the key space is something lengthy. Okay, I can also write like this. Let us take this structure. Okay, in this structure, what is the key here? The key here is 0, 0, 0, 0, 0, 0, 0, 0, 1 till 1, 1, 1, 1. 16 different values. For each value, 0, 0 is mapped onto one data. Okay, let it be 0, 0 is mapped onto 0, 0, 0 or 1. Okay. 1 is mapped onto 0, 1, 0, 0. Let it be 0, 0 is 0, 1, 0, 0, 1, 0. So 1, 1, 1 is mapped onto 1, 1, 1 is mapped onto, let it be 5. So this is 0, 1, 0, 1. So this is a data or key or transformation for this structure. Okay, so you have to remember this. Okay, so this much amount of data required to perform this transformation. Here, this is a 4-bit binary. Okay, if it is 16-bit binary or 64-bit binary, 64 different rows, for every row, the equivalent output pattern should also be remembered. Okay, this lookup to be remembered. Okay, so that's why for lengthy key size is required to design the unbreakable crypto system. 4 is inadequate, 6 is inadequate, and 8 is inadequate. So you have to use 128 or 64 or 256. If it is 256 or 56, 256, 2 power 256 factorial, it's a very good idea cipher, unbreakable. Okay, try all the transformation is not possible. But how much amount of data you have to remember? You have to remember n into 2 power n bits of data. Okay, n into 2 power n bits of data. Remember n into 2 power n bits of data every time. It's something utopia. Clear? Is it clear? Can you understand something about ideal cipher? Okay. So one more important point before getting into the thesis section. Symmetry ciphers are based on Shannon theory. Okay, I think I have given input already. It's based on Shannon theory. Okay, so what is that Shannon theory? If you take symmetry cipher, there are three things are involved. One is plain text in terms of bits, ciphertext in terms of bit string, and key is in terms of bit string. Everything is in terms of bit string, binary bit string. Okay, so hacker or intruder will try to find out, will try to exploit statistical relationship between these two. Okay, by exploiting statistical relationship. What is the statistical relationship? For example, the first bit, if the first bit is mapped onto the last bit, second bit may be mapped onto the first bit, just like this. Okay, so the statistical property to be exploited by the cryptanalyst to break the crypto system. Okay, statistical property or statistical relationship between the plain text and the ciphertext. Okay, for example, the third bit may be shifted or placed into the fourth bit. Okay, the third bit is reflector in the fourth bit of the ciphertext. The second bit of the plain text is reflector in the last bit of the ciphertext. So this is what the statistical property. So the crypton is, we'll exploit the statistical property, statistical relationship between the plain text and ciphertext to break the crypto system. Okay, so what we have to do here is we have to break the statistical property between the plain text and ciphertext. How? For example, if you take the first bit, okay, the first bit of the plain text. Okay, let me have the plain text 4-bit data. Ciphertext as 1010. The each and every bit should not affect one single bit of the ciphertext. Please listen to me carefully. Each and every input bit should not affect one single bit of the ciphertext. Okay, if it affects, then we have the statistical relationship between this bit and this bit that will be exploited by the hack. Okay, so to break this, each and every bit, its effect is dissipated or distributed to more than one bits. Okay, this bit will affect second bit, third bit, and fourth bit. Second bit of plain text will affect the first bit, second bit, and third bit. Okay, so more than one bit, not uniform manner. Okay, this effect is known as avalanche effect. Avalanche effect. Avalanche effect. Avalanche. Okay, you know the waterfall. So each plain text bit should affect or reflected in more than one ciphertext bit. Okay, perfect avalanche effect means each bit of the plain text is reflected in each bit of the ciphertext. That is a perfect avalanche effect. DS exploits the perfect avalanche effect. Okay, so to break the relationship between the plain text and ciphertext, okay, to break the relationship between the plain text and ciphertext, each bit of the plain text to be reflected or distributed, effect of the plain text is distributed to more than one ciphertext. Okay, so this property is known as breaking the statistical relationship between the plain text and ciphertext. This is known as diffusion property. Okay, this property is known as, based on Shannon theory, this property is known as diffusion. Okay, second important property is breaking the relationship between the statistical relationship between the ciphertext and the key. Okay, we have to break the statistical relationship between the ciphertext and key. Okay, so frequency analysis attack is one type of attack which is exploited based on this property. Okay, because the key is one such permutation. Okay, so for every permutation you are getting a different ciphertext. Okay, so breaking the relationship, statistical relationship between the key and the ciphertext is also important mandatory requirement for classical cipher. Okay, so that process is known as confusion. Okay, so confusion is one required property for symmetric cryptography. That means break the relationship between statistical relationship between ciphertext and the key. Okay, and another property is a diffusion. Break the statistical relationship between the plain text and ciphertext. Okay, so both are required, both are exploited. Okay, clear? Is it clear? Okay, so based on these considerations, Feistel structure is a design. Okay, so Feistel structure is based on the first property. What is the first property here? Feistel structure is based on the first principle, non-singular. Okay, it's reversible. It is based on the property called non-singular property. It's reversible. So second thing is that it should be ideal cipher like this. But the problem with this is there is a need to remember. Yeah, there is a possibility of 2 power n factorial transformation. So ideal cipher. So Feistel exploits this, but 2 power n factorial transformations are not possible because it is based on key. Slightly lesser transformations are possible, but based on this principle. Okay. So the third thing is that Feistel structure is based on confusion and diffusion property. Feistel structure is designed in such a manner that it exploits confusion property and diffusion property. So three things are motivation behind the Feistel structure: Shannon theory, ideal block cipher, and non-singular property. Okay, let's get into the Feistel structure. Any doubts so far? Okay. So feature section, it's not a cryptography, it's a structure. Okay, this is the base for DES algorithm. Okay, so in this feature section, it works on a block of data. There is an encryption process and there is a decryption process. Actually, it's all the symmetry, most of the symmetry ciphers are implemented in hardware. Okay, there is no separate hardware for decryption. Encryption hardware is used for decryption. The only one thing is that the order in which the key to be applied that should be changed. Okay, both encryption, decryption, both are same. So it takes a plain text of a particular block size. It produces a cipher text of the particular block size, and another input is okay. The decryption process, it takes a plain text of the particular block size and produces a cipher text, and the input another input. The input is a cipher text. Okay, same key to be used for decrypting the data. So cipher text is the input, plain text is output, key is the extra input. Okay, and it also based on a product cipher. Okay, a number of rounds to be applied. Okay, so what is a process? What is a stepwise operation? The feature section, the first thing is that first input is the plain text. Okay, so let me take a plain text. The plain text system, binary bit string. Okay, binary bit string represented in terms of power of 2. For example, we can take 16-bit plain text or 32-bit plain text, 64-bit plain text. Okay, the bit size, bit length to be represented in terms of power of 2. Okay, so they take it out the plain text first. Okay, so the plain text to be divided into the plain text to be represented like this binary bit string. Okay, so it's a binary bit string. Plain text is represented as binary bit string. Okay, so key is also a binary bit string. Okay, key is also represented as a binary bit data. Okay, so the first step here is the plain text to be divided into two equal halves. Okay, if it is a 32-bit binary, 32-bit binary, this is the first 16-bit data and this is the second 16-bit data. Okay, first 16-bit, second 16-bit data. Okay, and it's a product cipher. Every round it produces one output. So let's get into the name for this. The first 16 bits of the plain text is represented as LE0, represented by using one notation LE0. What is LE0? Simply first 16-bit of plain text, actual plain text. Okay, this is the right side part. Okay, most significant 16-bit of data. This can be represented as RE0. Okay. So this is a first round. We're going to apply round one here. Round one here. Okay. The output required here is again a same 32-bit data. Okay, divided into two equal half. Okay. So this side we need LE1 should be the output, and this side RE1 should be the output. Okay. So what should be this transformation? Okay. This is a one round function. What should be this transformation? Okay. So based on the feature section, the first 16-bit of data, okay, and second 16-bit of data to be treated in a different manner. Okay, so just to exploit substitution and permutation property. Okay, so feature structure is also known as substitution permutation network (SPN) architecture. Okay, so feature structure is also known as substitution permutation network. Substitution permutation network. Okay, or it is simply known as SPN architecture. It's based on SPN architecture, substitution permutation network. Okay, so the 16 first 16-bit to be treated in a different manner, second 16-bit to be treated in a different manner. Okay, so what we have to do here is take it out the next 16-bit of data, and here you have to apply a function. This function is known as round function, but this function is a binary function. It takes two input. Okay, one input is the 16-bit plain text data RE0. Another input is also required. Okay, that input is key, because in order to exploit the confusion property, the key should also be distributed in each and every round. Okay, so here we are not going to use the key. Actually, our key is K. Okay, see, let's see. The key is K. Okay, now I'm going to use the different thing. Okay, here I'm going to use a key that is K1. What is this K1? K1 is not a key, but K1 is a sub key. Okay, so from the key K, we have to generate n number of sub key. Okay, that is based on sub key generation algorithm. Okay, so one such key is K1 sub key. That should be the input here. Okay, so one input is RE1, another input is K1. Okay, so this is a bit of size 16-bit. If it is 16-bit binary data, this should also be 16-bit data. Okay, this should also be 16-bit data. Okay, if the input, this input is 32-bit input, this one should also be 32 bits. Okay, the function of text to input, one is the right side component of RE0 and another one is self. Okay, so then this one to be XOR. XOR is a binary bitwise operation. Okay, simply 0, 0, 0, 1, 1, 0, 1, 1. Okay, if both the bits are same, what is the output? XOR, XOR truth table, 0, 0. What is the XOR truth table?
0, ma'am. 1.
11. So 1, 1, the output 1, 1 is also 1, 1. For these two things, it will be 0, 0. Actually, it is based on a simple mathematical property called modulo 2 arithmetic. Okay, I will tell you later. So simple XOR operation. XOR is also a binary operation. It needs two input. Okay? One input is the output of the round function. Another input is this. Okay, another input is this. Okay, so after this XOR operation, the result is again 16-bit, not 32-bit. Okay, so the result is a 16-bit of RE1. Okay, so I'll write it out the equation form, linear equation form. What is RE1? RE1 is equal to, I'll write it out. RE1, okay, so RE1 is equal to, based on LE0, LE0 XOR, okay, and function of RE0, comma, K1. Okay, so this is a linear equation for this. But what about this 16-bit data? Okay, because this 16-bit data uh, 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 that should be filled. Okay, then only the subsequent transformation can be applied, can be performed properly. Okay, so the first 16-bit data is a direct. This operation is known as permutation. Okay, this operation is known as complex permutation. Sorry, complex substitution. Okay, now this is to be filled by a direct permutation. Okay, so now this one to be filled by this data directly. Okay, so I'll write it out in the linear form, equation form. What is LE1? LE1 is a direct substitution data. Okay, direct permuted data. LE1 is equal to LE1 is equal to the same right side component RE0. Okay, so can you understand this round one alone? Round one input is 32-bit data divided into equal half 16, 16. Just apply permutation on right side 16-bit data, substitution on left side and right side 16-bit data. So RE0, LE0 and K1, all these three elements to be used to compute RE1. Okay, RE1 is based on left side 16-bit data, right side 16-bit data and K1. Okay, and the first 16-bit to be filled directly by OC is simple permutation. LE1 is equal to RE0. Okay, so it's a product cipher. Same operation to be repeated again and again. Okay, so now I'll get into one more round alone. Okay, I'll get into one more round. Yes, go for one more round. Okay, so for this, this is actually round two. Okay, round two. Output, expected output is 32-bit output, that is LE2 RE2 padded with RE2. Okay, now this is applied to the same function. Okay, all the functions are symmetric in nature. So for this function, one input is here and another input is, okay, here I have used a K1. I say the K to be converted into 16 different subkeys. Okay, so here I have to use another second key, sub key K2. Okay, and both to be given to the function F. And finally, we have to do XOR operation. For that XOR, this is also LE1 is the input, produces the output. Okay, now this is directly substituted here. So for this equation is LE2 is equal to RE1, okay, and RE2 is equal to LE1 XOR with F of RE1, comma 2. Okay, clear? Clear?
Yes, ma'am.
Okay, now we directly get into the 16th round. Okay, now other rounds, subsequent rounds. Now the final round are 16th round. For 16th round, what will be the input? The input will be, input is, for 16th round, the input is LE50, RE50. Okay, sorry, RE50. Output will be, output will be LE60, RE60. Okay. So this is RE50. Now the expected output is, output will be LE16, RE16. Okay. Now the round function, this one to be given to the round function F. Okay. Another input is required. Here I have to use K16, 16th sub key, and that one to be XORed with this. You will get RE60. Now this input to be given to this. Now this is LE60. Okay. So let it make a general equation for this, a single common linear equation. Okay. So LEI, okay, is equal to REI, REI minus 1, because LE2 is equal to RE1. Okay, so LEI, ith round left side component is equal to I minus 1th round right side component. Okay, direct right side component. Okay, general equation in general, I is equal to 1 to, sorry, I is equal to 0 to 15. Sorry, 1 to 50, because 0 is the input. Okay, so 1 to 50. So LE1 is equal to RE0, LE2 is equal to RE1, and so on. Okay, now the second thing, REI is equal to LEI minus 1 XOR with a function of REI minus 1, comma KI. Okay, KI. Can you understand this? This is a general equation for PC sector encryption process. Just a simple linear equation. Can you understand this? Clear? Clear? Is it clear?
Ma'am, is it mandatory that in all the 16 rounds the key should be compulsory different, ma'am?
All the 16 rounds are same, symmetry. Same.
Like you said that K1, K2, K16 all should be
Parameters are different. Okay, good question. The function remains same. Okay, the function remains same, but the parameter K is different. Okay, the K should be different. It is compulsory because to exploit the confusion property. Exploit the confusion property. Because what is the confusion property? The statistical relationship between the key and the ciphertext to be removed. Okay, to remove the statistical relationship, every round should be based on different subkey. It's not a key, it's a subkey. The user need not remember the key. From K, you have to generate 16 keys. That is also part of the symmetric cryptographic algorithm. Okay, if you give us a 56-bit input, DS is based on 16 48-bit subkey. Okay, but you need not remember the key. If you give an input as key, okay, it's also another. We have completed only one process. Okay, see, not yet completed. You have one more thing to be completed. This process is in symmetric pieces structure. This is a encryption process. Encryption process. I have not yet completed. We have one more operation to be performed. What are the remaining two pending things? Another one is decryption process. You need to know what is decryption. Another one is it sub-key generation. Okay, sub-key generation algorithm. That is, the input will be the key. Sub-key generation algorithm. The input will be the key k of a fixed size. Output will be 16 key, n number of keys, k1, k2, k3, k4, and so on. That is also based on Shannon key. Okay, so it's mandatory to have unique sub-key for every round. It is mandatory. It's compulsory to exploit confusion.
Okay, ma'am.
Clear? Any more doubts? Can you understand this equation clearly? But yeah, this is for the design. Okay, I have not given what is F. F can be anything. You can use F as any function, any coding function. Okay, and but thing is that you have to pass these two parameters as a these two element as a parameter. That's it. Okay, if you can understand pieces structure clearly, just by exploiting some of you, I think you know coding technique. IT student, you know coding technique. By exploiting coding technique, you can design your own Feistel structure based cryptography. Okay, but we have some metrics to evaluate the security strength. I will tell you at the end. Okay, but it is not yet over. Encryption process. What we have seen so far. What we have seen so far? The input is a plain text. Okay, the input plain text is divided into two equal half. Okay, and the second half is given to one transformation. First half is given to another transformation, and we have 16 different rounds. Number of rounds important. If number of rounds are high, security strength is high. Number of rounds are low, security strength is low. Okay, AES today's minimal standard is 10 rounds. Okay, actually 10 round AES is available, 12 round AES is available, 14 round AES is available. Okay, so 10 round AES is a minimal standard. Okay, but the researchers are working on breaking AES crypto system. By using quantum computing power, we can break AES with 8 rounds. Okay, so what is the difference here? 8 round AES is breakable, but 10 round AES is not breakable. Okay, number of rounds matters. If number of rounds are high, security strength is high. Okay, so here we have 16 rounds. In every round, we are using one sub-key, final transformation E16 and RE16. In symmetric cryptography, one thing is important because symmetric cryptography, most of the symmetric cryptography are implemented in hardware. Hardware is vulnerable to one important attack called a side channel attack. Okay, but I'm not going to talk about side channel attack now because to understand side channel attack, we need a 15-20 minutes of time. We'll talk about side channel attack, device attack, masquerading attack, all type of active attack, passive attack in the later class. Okay, because the first part of the first unit is not a starter. Okay, so to avoid side channel attack, we need to do some sort of transformation at the end. Okay, you have to make some sort of confusion at the end to avoid hardware attack or side channel attack. Okay, so that is also very simple. Simply just doing a permutation, just a swapping. Okay, it's a simple swap operation, 16-bit swap operation. This is swapped here. Okay, this one will be swapped here. So this will be RE17, not based on any key. Okay, simply a swapping. This part is RE17. So cipher data is okay. The input is the plain text is. I can represent the plain text as this LE0 padded with RE0 because the first 16 bit is LE0, the second 16 bit is RE0. So plain text is nothing but LE0 padded with RE0. Okay. What about the output? Output is cipher output. So this is LE17 padded with RE17. So the encryption algorithm transforms the data LE0 padded with RE0, that is a plain text, to LE17 padded with RE17, that is a ciphertext. Okay. Now the decryption algorithm should do the reverse process. Okay, we have to reverse back. LE17, RE17 will be the input. The ciphertext will be the input. Okay, we have to reverse back. to get back this plain text. Okay, so that algorithm is a decryption algorithm. Still now, is it clear? Any doubts so far? Is it clear?
Ma'am,
Yes.
like, is there any possibility where RE1, RE2 may coincide, ma'am? Like REI and REI plus 1, like that. Yeah.
RE,
Suppose RE2 and RE3 are same. Like that,
RE2,
it may
RE,
happen, ma'am.
RE2, RE may happen. But
It may
what's the
happen.
problem in that?
Just asking, it may happen or not. Like, will they be unique or they can be similar?
Maybe unique or may not be unique, but what sort of security violation here? Is it by exploiting that property? Is it possible to break this key
No,
by
ma'am, because
exploiting
key is
that
unique.
property? Key is unique, by
Uh-huh.
exploiting that property, maybe sometimes the bit pattern may coincide. All the bit pattern may be zeros, all the bit pattern may be one. Okay, but the thing is, that's why the thing concept is breaking the statistical relationship between the plain text and ciphertext. Ciphertext to plain text is a motivation, it's a requirement. Okay, you do
Okay,
not
ma'am.
think in terms of binary bit data, zeros and ones. Don't think
Okay.
about zeros and ones.
Okay.
Sometimes LE1 may be equal to RE1, LE2 may be equal to RE2. That's not at all a matter because it's unbreakable. We are breaking the relationship between the original plain text and the ciphertext.
Ma'am, if then suppose the key is full of ones or full of zeros.
Which key?
K.
K is a user given data. K is
Huh.
can be full zero, full one, or zero, any combination. K actually, P is a structure. If the key is a 16-bit key, any bit pattern of 16-bit can be full zeros or full one or any combination. It will work out properly. Even the K is full of zero, the K1, K2, K3 will be something different. Okay, because subkey generation algorithm is based on again substitution. There is a substitution. So 0 may be replaced by 1. So you won't get all zeros in K1, K2, K3. That will be something
Oh,
different. It's a
okay.
complex generation algorithm.
Yes, ma'am. Okay.
Even with all 0, you will get different output.
Oh, okay, ma'am.
Anything else? Any other doubts? Please try to understand the structure in such a manner that you can apply it or you can design in the new crypto system. Okay, that is a way of learning cryptography. Learning cryptography doesn't mean that learning something which is already existing. Okay, you can exploit your ideology here, you can innovation here, you can put your effort here to design a new type of crypto system. That is what I require. That is what others expect. Okay, I'm not going to start a decryption now. I will upload this video today itself. Please go through this video again. Tomorrow, we are going to discuss about decryption process. Decryption with the example of Feistel structure, not DES. Okay, so the complete understanding of Feistel structure is required to understand DES as well as AES, and we have many number of symmetric cryptosystems, many more symmetric cryptosystems like TLS, transport tower security is based on Camilo symmetric structure and Bluefish symmetric cryptography. All those symmetric cryptographies are based on Feistel section. It's based on Feistel section. Okay, all the successful symmetric cryptographies are based on only Feistel section. So the complete understanding of Feistel section is important. So tomorrow we'll continue with the Feistel section with the decryption process, and we work out some problems based on Feistel section. Then we continue with the DES. Okay. So I'll stop here. If you have any more doubt, you can ask. This paper is not a project-based paper. Even it is not a project-based paper. If you are interested in doing